Okay, thank you very much for the invitation to this wonderful conference and giving me the opportunity to give you a brief summary of what I've been working on in the last year. This talk is based on a collaboration with Dong-Woo Kim, who is here, and also my student, Min-Sung Ko, as well as some work that we have been put out with Norton Lee, who is in Pohang, and as well my student, Min-Sung. So the overall theme of the workshop is this picture. I also have a picture here. This picture it's representing some landscape. And here, the meaning of this picture is basically the interaction between geometry, how geometry tells us about supersymmetric gauge theories, how supersymmetric gauge theories are realized by strings and branes, and how these strings and branes form configurations based on geometry. So I will talk about these three concepts during this talk, and we can ask several questions in this relationship, and I will tell you a little bit at the beginning of my talk how gauge theories connect to geometry, in particular supersymmetric gauge theories, how their moduli space forms various interesting geometries that are studied in mathematics. In our case, these geometries are complex geometries, Calabi-Yau manifolds, and gauge theories can, in our work, be considered as world volume theories of d-branes that probe non-compact Calabi-Yau singularities, conical singularities. So these can be Calabi-Yau free-folds. Then the singularity is probed by a d3 brane. The world volume theory is a 4-dimensional n=1 theory. If the Calabi-Yau is a non-compact Calabi-Yau 4-fold, then the singularity is probed by a d1 brane. The world volume theory is a 2d0,2 theory. And recently, we have been also looking into Calabi-Yau 5-folds. And there, the world volume theory is on a d-1 brane, probing the singularity of the Calabi-Yau 5-fold. As a review of what we have been doing for the last decade, let me first focus on the simplest case where the free branes probe a Calabi-Yau 3-fold. Here, the Lagrangian of the corresponding 4D n=1 theory contains two main components that determine the vacuum moduli space of those 4D n=1 theories, which precisely for the abelian case, abelian theory is the Calabi-Yau 3-fold itself. The meta content of the 4D n=1 theory in terms of chiral fields forms a coordinate ring subjected to a set of relations that come from the F terms of our 4D n=1 theory. These F terms are restricted to be binomial relations. So under this restriction, the Calabi-Yau 3-fold becomes a toric Calabi-Yau 3-fold. And overall, we also take a GIT quotient subjecting everything to gauge invariance so that the vacuum moduli space is simply the space of all gauge invariant operators that form a non-compact manifold, precisely the Calabi-Yau 3-fold in the case of abelian gauge groups. So the data obtained from the Lagrangian comes from the chiral multiplets as well as the superpotential. Those objects from the Lagrangian can be encoded in a Quiver diagram where the nodes correspond to gauge groups, the arrows correspond to the bifundamental chiral matter, and then loops that are either clockwise or anti-clockwise oriented correspond to superpotential terms, gauge invariant terms in the superpotential. Another interesting analogy to understand this configuration is to take a T-dual transformation on the branes that probe the Calabi-Yau 3-fold. If I do T-duality along two directions, the D3 branes become D5 branes suspended between an NS5 brane wrapping holomorphic curve. In this case, this curve parameterized by two complex coordinates. This curve is also what we call as a mirror curve of the Calabi-Yau threefold, and it's given by a zero locus of a polynomial in terms of x and y. We will later talk a little bit more about the origin of this mirror curve and this Newton polynomial encoded in the geometry of the Calabi-Yau threefold. The neat thing here is that knowing this holomorphic curve or this mirror curve tells me exactly how the brane configuration made out of D5 and NS5 planes looks like. If I project this curve onto the torus, I can then have a picture, a brane configuration on the two torus made out of D5 and NS5 planes. The location of the curve tells me where the NS5 is intersecting with the two torus. And then I have areas where the NS5 plane is not present, and these areas are where, or these enclosed boxes are where the D5 plane is suspended between the NS5 plane. So this picture is really the type 2 brane configuration from which I can actually read off the matter content as well as the interaction terms of the corresponding 4D n=1 theory. And in fact, for the last 15 years, there has been a collection of various different works related to this brane configuration. The mathematical interpretation and the brane interpretation of this picture is really encoded in what we call a dimer model or brane tiling. It's a bipartite graph for the two torus that encodes the superpotential and the chiral matter content of the corresponding 4D n=1 theory. I will not talk too much about brane tilings in this talk, but it's an indication of how we in the large families of 4D n=1 theories, the Calabi-Yau geometry is encoded as a vacuum moduli space. We have been doing this since I was a graduate student. We have been classifying the corresponding moduli spaces for large families of 4D n=1 theories corresponding to toric Calabi-Yau threefolds. One of the largest classifications was this set of 30 4D n=1 theories associated to brane tilings and toric Calabi-Yau threefolds. If I represent these brane configurations in an abstract form, each box here represents a distinct 4D n=1 theory. And for each of these 4D n=1 theories, you can compute the corresponding moduli space. And one interesting thing here is that some of the moduli spaces of distinct 4D n=1 theories are identical to each other. And that means in the 4D n=1 case, that corresponds to duality, Seiberg duality, to be precise, where these 4D n=1 theories share the same infrared fixed point. So I have two different theories with two different Quiver representations, two different brane configurations, and they, as 4D n=1 theories, are expected to have the same infrared fixed point, meaning that they have the same vacuum moduli space. So when we look at families of 4D n=1 theories, they on the surface do not look like as if they are related to each other. But if we look closer into the geometry encoded into the gauge theories, we see that there are non-trivial relationships between them. And we have been pushing that even a little bit further. That was also a few years ago. In fact, there are further relationships between those different 4D n=1 theories. A different relationship, which we called specular duality more than 10 years ago, was a relationship between 4D n=1 theories that not only share the vacuum moduli space, but they share a different moduli space, which we refer to as the master space. So you can think of this master space as a larger space containing the Calabi-Yau vacuum moduli space. It's the same quotient that you take in terms of the chiral multiplets and superpotential relations without the gauge invariant quotient here. So these gauge invariant, the U1 gauge groups become in the limit of the infrared baryonic symmetries. And without taking the quotient under these baryonic symmetries, the spectrum of gauge invariant operators are not only what we call mesonic, but also baryonic because they contain baryonic charges. So this space of gauge invariant operators is what we call as a master space containing the regular vacuum moduli space corresponding to the Torrey-Calabi-Yau threefold. So in that context, some of these 4D equals 1 theories share the vacuum moduli space, but some of them also share the larger space, the master space between those as moduli spaces. So there are more relationships. Now, you can do this game also in the opposite direction, right? I mean, if you have a family of 4D equals 1 theories, you can compute the moduli spaces of them and try to understand the relationship between those moduli spaces and try to interpret the geometric meaning of these moduli spaces. But you can reverse the question. If you have a class of geometries, what are the corresponding gauge theories associated to them? So if you do that, that was something we started to do last year, then we see that in this family of 30n equals to 1, 40n equals to 1 theories, there are further relationships that originate from some new properties that Torrey-Calabi-Yau threefolds have. This property referred to as birational equivalence. So that will be something that I will talk more deeply about, what it means to have a birational correspondence between different toric varieties associated to Torrey-Calabi-Yau threefolds or higher dimensional Calabi-Yaus, and what that interpretation of correspondence in the algebraic geometric sense means in the context of the corresponding Quiver gauge theories. So one important thing here is that we restrict ourselves to Calabi-Yaus that are toric. Toric Calabi-Yaus are characterized by lattice polytopes. In the case of Torrey-Calabi-Yau threefolds, these polytopes are two-dimensional. And there are many families of such geometries. One of the more famous ones in algebraic geometries are the so-called Fano twofolds. They are parametrized by a finite set of very particular polytopes on the 2D lattice. These are convex lattice polytopes that have a single interior point. They are known as reflexive polytopes, and the associated toric varieties are known to be Fano. In higher dimensions, the corresponding Calabi-Yaus are four-dimensional, and you can then also generalize Fanos into Fano threefolds, and the corresponding toric diagrams have are three-dimensional and have one internal point. And in fact, there is a theorem that in any dimensions, the number of reflexive polytopes is finite under modular equivalence. And the classification was done by Kreutzer and Skrake up to dimension 4, that in dimension 2, corresponding to Calabi-Yau threefolds, there are 16. In dimension 3, corresponding to Calabi-Yau fourfolds, there are over 4,000. And in dimension 4, there are over 400 million that correspond to Torrey-Calabi-Yau fivefolds. So this is a very nice set of geometries we can start from and ask the question, what are the corresponding Quiver gauge theories living on branes that probe the corresponding Calabi-Yau singularities, and what properties of these geometries can be interpreted as properties of the corresponding gauge theories. Mm-hmm.
Reflexive regular ones are supposed to maybe represent the equivalent classes of modular distributed ones?
No, no. So the regular cases are corresponding to smooth Fano variant. No, that's a different concept. Yes, yes. So in terms of the polytopes, regular means that there are no internal points on the boundary of the polytope except for the extremal vertices. So in the dimension 3 case, there are 18 of them, which is a subset of the 4,300 that you have. That's a very good point. So here, given such a toric polytope, I can extract the so-called Newton polynomial out of it. The Newton polynomial is simply the generating function of the vertices. In the case of a two-dimensional polytope, this Newton polynomial is parameterized by two complex coordinates x and y. And the zero locus of this Newton polynomial is precisely the mirror curve that I was mentioning earlier when we were talking about the brane configuration dual to the probe branes at the Calabi-Yau singularity. And the complex coefficients of this polynomial are in the context of the mirror curve side corresponding to what we call complex structure moduli. So as I said earlier, when we had the D3 brane probing the Calabi-Yau threefold, if I T-dualize it, I have a D5 brane suspended between an NS5 brane wrapping this curve, and this curve is then defined by the zero locus of the Newton polynomial of the associated toric diagram of the Calabi-Yau threefold that I start with. So now the question is, given that information, the toric data of the toric Calabi-Yau threefold, what are the corresponding gauge theories that I can construct? We call this process the inverse algorithm because we start from the geometry to identify what the corresponding gauge theories are. And there are many different avenues of how you want to answer this direction. And one approach was to use AI. So I have been doing AI for a while now. And last year I was implementing a generative AI model, a so-called variational autoencoder that takes the complex structure moduli of a given mirror curve and generates the corresponding brane configuration associated to the shape of the mirror curve. In fact, how do I see the shape of the mirror curve? I simply take the zero locus of the Newton polynomial for a particular choice of complex structure moduli and project it down onto the two torus. That's the two torus on which the NS5 and D5 brane configuration map into a brane tangling picture on the two torus. That's the two torus where the D5 branes are represented by enclosed faces, where the boundary of the enclosure is the NS5 brane intersecting with these two torus. So what you can do is you can try to solve this equation by, let's say, a Monte Carlo method. And each of the solutions found stochastically can be mapped to their angular coordinates. And every black dot here represents one particular solution to this equation projected onto the two torus. So the darker areas represent where the NS5 brane is intersecting with the two torus, whereas the white regions represent where the D5 brane is suspended between the NS5 brane. And what you can now do by training this AI model is that now you can continuously change the complex structure moduli and see how the mirror curve changes when it's projected onto the two torus. And with various steps, you can now identify what the corresponding dimer model as well as the corresponding 4DNX1 model, 4DNX1 gauge tree should look like. And you can really see that at some values of the complex structure moduli, the theory changes to another theory. So you can actually visualize by continuously changing the complex structure moduli how one gauge theory maps to another gauge theory by a transition, which is in this case exactly Seiberg duality. Right? So that was one thing, one approach to answer this question, going from geometry to gauge theory. I want to tell you a little bit about another approach that really leads us to the main topic of my talk today. And that approach is based, initially started by looking at one dimension higher to look at Calabi-Yau fourfolds that are much richer geometrically than Calabi-Yau threefolds. And we started looking at Calabi-Yau 4 folds associated to a family of 2D 0,2 theories. Calabi-Yau 4 folds have been studied more closely by mathematicians, and that really led us to identify new properties of geometries that are associated to the corresponding gauge theories. And then we were able to reinterpret those properties in the lower dimensional case as well. So in order to talk a little bit about Calabi-Yau 4 folds, we do the same exercise. I have a toric Calabi-Yau 4 fold whose polytope is given by a convex lattice polytope in 3 dimensions. The corresponding Newton polynomial, again, is a generating function of all of its vertices, now parameterized by 3 complex coordinates because I have a 3-dimensional polytope. The zero locus of that Newton polynomial, again, defines what we call as a mirror surface. That's the analog of the mirror curve of the mirror Calabi-Yau 4 fold in this case. And now you can do the same job. I mean, for a particular choice of complex structure moduli, I can try to project it onto a 3 torus. And that is really the same thing that you would do when I have my D1 brane probing the toric Calabi-Yau 4 fold. I can T-dualize now this configuration in 3 different directions. This should be a D4 here. And when I T-dualize this in 3 different directions, the D1 brane becomes a D4 brane suspended between an NS5 brane, wrapping now this holomorphic surface sigma coming from the zero locus of this Newton polynomial that I obtained from the 3-dimensional toric diagram that I have from the toric Calabi-Yau 4 fold. So I can project it onto the 3 torus. The 3 complex coordinates have 3 angular components. If I project it onto the 3 torus, every solution to this zero locus equation will determine the position of the NS5 brane wrapping this 3 torus here. And every empty region bounded by the NS5 brane, that empty region should locate the D4 brane that is suspended between the NS5 branes that I highlight here as a projection of the mirror curve, mirror surface. So we, in fact, that was what we did now nearly 10 years ago with Sangmin here and also Sebastian in New York, where we reinterpret that as a combinatorial object on the 3 torus, really the analog of this projection of the mirror surface onto the 3 torus, which we call as a brane-brane model. This is the higher dimensional analog of the brane tiling that we had for 4D n=1 series associated to Calabi-Yau 3 folds. These brane-brane models are basically tessellations of the 3 torus, where polytopes represent the locations of the D4 brane, and boundaries of these polytopes represent this NS5 brane wrapping this 3 torus. It's really the simplified version of this figure that we have here. And now the D4 brane gives rise to a UN gauge or UN gauge group in my corresponding 2D 0,2 theory. And now the boundaries of these polytope, which can be oriented or unoriented, correspond to either a fundamental or anti-fundamental chiral multiplet of the 2D 0,2 theory associated to this gauge group represented by this polytope here. We can also have faces that are unoriented, and these faces correspond to another multiplet that exists in 2D 0,2 theories, which is the Fermi multiplet. So in total, I can represent a gauge group and its associated chiral and Fermi multiplets in terms of what we call here as a brane break. And this object then tessellates these 3 torus without leaving any gaps. And its periodicity then encodes the Lagrangian of the associated 2D 0,2 theory. So not only the Fermi and chiral multiplets, but also their corresponding interaction terms. So every edge associated to a Fermi multiplet is connected to a family of chiral multiplets, and reading from the connectivity of this tessellation, I can read off associated interaction terms to the Fermi and conjugate Fermi of my 2D 0,2 theory. These interaction terms in the 2D Lagrangian are known as E and J terms, and these are precisely encoded in the combinatorics of this graph here. So for every Fermi, I have a J and E term, and the combinatorics of our brain-brain model tells me precisely what the associated 2D 0,2 theories are. And now you can really see the connection here, how geometry is leading us to the corresponding 2D 0,2 theory. If I really change the complex structure moduli, the surface intersecting with the free torus will change. The shape of the brain-brain model here will change, and we will end up under transitions that give me a new gauge theory when I pass through some phase boundaries between different phases of the 2D 0,2 theory associated to the same Torre-Calabria fourfold. This is in the 2D 0,2 case known as a triality and has been studied by Gade, Gukov, and Putrov initially, and we have papers on that as well, which is not the topic of my talk today here, unfortunately, but you can see that the analog here will happen as well in the context of Torre-Calabria fourfolds and 2D 0,2 theories. The important thing here is that given a brain-brain model, the matter content, the interaction terms, again, can be represented as an algebraic variety. The J and E terms are all binomial, giving me a toric variety weighted under the one gauge charges of my 2D 0,2 theory. If I quotient them out, I get a spectrum of gauge invariant operators subject to the J and E terms, which is precisely the Calabria fourfold that is probed by the D1 brain here. As a comparison to 4D n equals to 1 theories represented by brain tilings, the only additional information that I really have here is in terms of Fermi multiplets that now label pairs of analogs of F terms in 2D 0,2 theories, which are called J and E terms. So here is an example. I have the cone over Q111 over Z2, which is a Fano threefold. The corresponding toric diagram is this dual pyramid. The corresponding Newton polynomial is of this form, and you can see that the matter content is encoded in its quiver, and the interactions are all binomial given by these J and E terms. And you can clearly see that if I look at the quiver diagram, I have every Fermi is associated to two pairs of directed paths, which correspond to either an E term or a J term inside the interaction terms, inside the Lagrangian of the 2D 0,2 theory. Yeah, so this is the picture that we have. So that's the data that we are looking at. We have the geometry of the Calabria, the quiver, and the J and E terms that uniquely determine the corresponding 2D 0,2 theory. Another example is this toric Calabria fourfold. The associated quiver diagram is this, and the corresponding J and E terms are given by this. And you can now compute the geometry of the Calabria fourfold by computing the algebraic variety that I showed you earlier. So here, it's again, I have this looking at geometry, the geometry of toric Calabria fourfolds, and gave you an idea of how we generate associated 2D 0,2 theories whose vacuum moduli space is given by this toric Calabria fourfold that we start with. But yeah, so one thing that we can do is you can look at the families of Calabria fourfolds, let's say the smooth Fano threefolds, and try to find all of the associated 2D 0,2 fields. That's one thing that we did in a paper with Sebastian Franco a couple of years ago. But one thing that I want to mention today is that these Fano threefolds have been also studied systematically by a group of mathematicians in 2012, Akhtar, Coates, Rak-Kyeong, and Kasprets. And they identified that these reflexive polytopes associated to the 4,318 Torre-Calabria fourfolds that are Fano threefolds are not truly independent to each other. In fact, if you look at the corresponding Newton polytope or the associated mirror surface of the Calabria fourfold, they saw that if I look at the three complex coordinates x, y, and z, you can introduce a birational transformation on the complex coordinates x, y, z that leads us to a new Newton polynomial, which as a Newton polynomial is associated to a new polytope that is not the same as the previous polytope that you started with. In fact, in addition to some modular transformation, you can clearly show that these two resulting polytopes, so I start with an original polytope with an original polynomial, then do the birational transformation on the three complex coordinates, giving me a new Newton polynomial and a new polytope. And these two polytopes are not identical under a modular transformation, but they are associated to two toric varieties that the mathematicians claim are continuously deformable into each other, meaning the two toric varieties are so-called birationally equivalent to each other. And what Coates and colleagues have done in 2012 was look at these 4,319 reflexive polytopes in dimension 3, and they showed that out of these 4,319 Newton polytopes, 3,225 of them have an associated birational transformation that subdivides these 3,025 polytopes into 165 equivalency classes. In fact, one equivalency class is this pair where I have two reflexive polytopes corresponding to two Torre-Calabria fourfolds that are related by a birational transformation that maps the corresponding Newton polynomial and mirror curve into each other. And in fact, they call these equivalency classes buckets, and they basically showed that 3,025 of these reflexive polytopes give rise to 165 mutually independent equivalency classes under these transformations. So the question really was, what does this mean in the context of the associated 2D 0,2 theories? In fact, when we look at the particular example of a bucket where I have a Newton polynomial of this form, the birational transformation gives me this polynomial that can be simplified under a modular transformation to this polynomial here. You can clearly see that these polynomials give rise to these two polytopes that are not equivalent to each other by a modular transformation, but claim to be birationally equivalent due to the fact that their toric varieties are deformable into each other. So what mathematicians claimed in the algebraic geometry side of this question is that these two toric varieties associated to these two polytopes connected by a birational transformation have the same period. So you can compute the period of any variety by looking at its defining characteristic polynomial using this formula. And one of the invariants of this transformation is that these two toric varieties share the same period. And in the string theory context, the period is basically connected to the generating function of Gromov-Witten invariance associated to this manifold. Another object that they identified to be an invariant under this transformation is the so-called Erhard polynomial. It's basically a generating function of lattice points when you n-fold enlarge the lattice by a scale of n. So that's so the number of vertices for n-modulated lattice is identical for these two polytopes. And as I said earlier, these two toric varieties are deformation equivalent into each other, meaning that there exists a continuous fiber that along which these two toric varieties are connected to each other, and along this fiber you can have a continuous deformation that maps one variety into each other. So these were the three mathematical properties of this birational equivalence. And now the question was, what are the consequences of these mathematical properties in the context of the associated 2D 0,2 theories? How are the corresponding quiver gauge theories related to each other? And can we go, a secondary question that we wanted to answer was, can we go beyond toric Fano three-fourths corresponding to reflexive polytopes? Are there corresponding transformations that not only relate reflexive polytopes, but more general lattice polytopes associated to more general toric Calabi-Yau four-folds? And that was the initial project that we did last year with Dongok here and my student. And what we did was we identified the corresponding 2D 0,2 theories and saw that just by looking at the quiver diagrams associated to the 2D 0,2 theories corresponding to these two toric Calabi-Yau four-folds mapped to each other by this birational transformation are related by just a removal of Fermi-chiral pairs in the quiver diagram. In fact, if you look at these Fermi-chiral pairs and remove them, you get the quiver of the dual theory associated to the Calabi-Yau four-fold that is generated by this birational transformation. And these Fermi-chiral pairs, when you look at the corresponding interaction terms, really correspond to so-called J and E terms that can be integrated out when I add mass terms to them. And so in fact, this is in the context of 2D 0,2 theories, a mass deformation where I can get rid of Fermi-chiral pairs in the original theory and generate, by integrating out these new mass terms, a new theory that is associated to a toric Calabi-Yau four-fold now that is related to the original toric Calabi-Yau four-fold by this birational transformation. So now you can ask, is every birational transformation a mass deformation in the 2D 0,2 sense? And the answer is not precisely. In fact, the claim here we are doing is that birational transformations are more general than mass deformations. Every mass deformation that we can do in the corresponding 2D 0,2 sense has an associated birational transformation, but the reverse is not necessarily true. That makes this correspondence between birational equivalent toric varieties quite interesting. In fact, so one conclusion of our exploration was that mass deformation of 2D 0,2 theories relates to a birational transformation of the associated toric Calabi-Yau four-folds, but the reverse is not necessarily true. How about looking a bit deeper? If I now actually go into the algebraic description of the vacuum moduli spaces of these 2D 0,2 theories, I can compute something called the Hilbert series, which is the generating function of the gauge invariant operators that parameterize the moduli spaces of these 2D theories. And I can, as a general Hilbert polynomial, I can rewrite the generating function in terms of a particular weight assignment of the associated coordinate ring. What does that mean? I can redefine this partition function in terms of orthogonal choice of fugacities that make these two Hilbert series identical to each other. What does that mean? Right? Usually, these fugacities count charges carried by these gauge invariant operators under the global symmetry of the 2D 0,2 theory, the global symmetry including mesonic symmetries and the U1R symmetry. I can turn off the non-R symmetry fugacities and set them to 1 and just leave with the fugacity that counts the U1R symmetry associated to these 2D 0,2 theories. When I do that, this magic happens that the two Hilbert series are identical to each other, meaning that the birational transformation linking these toric-Calabi-Yau 4-folds somehow maps the U1R symmetry or the information encoded under this U1R symmetry inside this Hilbert series into each other for these two different theories associated to these two toric-Calabi-Yau 4-folds. So the second conclusion that we had was that the U1R symmetry refined Hilbert series remains the same for the 2D 0,2 theories related to toric-Calabi-Yau 4-folds that are birationally equivalent to each other. Last but not least, a consequence of the previous observation using Hilbert series is that I can actually compute the generators of the spectrum of gauge invariant operators, and the generators themselves, when I represent them as vertices in a three-dimensional lattice, where each coordinate of a lattice point is basically the rank 3 global symmetry charge carried by each of these generators. These lattice of generators, or the number of generators in these lattices, are an invariant of this transformation, meaning that the moduli spaces of these 2D 0,2 theories associated to birationally equivalent toric-Calabi-Yau 4-folds have always the same number of generators for the spectrum of gauge invariant operators forming the moduli spaces. So the third thing here is that the number of generators of the moduli space remains the same. So these are three observations that we have been making since we started working on this last year. And the story seems to be quite rich. In fact, there are many Calabi-Yau 4-folds, many interesting mathematical properties that the mathematicians have been digging out from there that have very interesting interpretations in terms of 2D 0,2 theories related to these toric-Calabi-Yau 4-folds. So geometry, when I go from geometry to the associated gauge theories, it tells me some non-trivial structure that we are not able to see by just looking at the gauge theories themselves. Relationships between geometries seem to have very interesting properties in the context of toric, in terms of the context of the corresponding Quiver gauge theories. And, the latest direction that we are looking at here is that we, in fact, these birational transformations not only restrict themselves to the reflexive case. In fact, we showed that birational transformations of toric varieties associated to non-reflexive polytopes in Z3 are also mapped into each other. In fact, such birational transformations also exist, and in fact, you can then show that the associated toric 2D 0,2 theories again are related by a mass deformation. In fact, that's one work that we did very recently, and again, not only mass deformation, the U1R symmetry refined generating functions of the gauge invariant operators are also identical to each other, and the number of generators, in this example 50 generators, are shared between these two these 0,2 theories. Yes? Mm-hmm. Very good question. So here the gauge invariant operators carry U1R symmetry charges that are irrational. So in order, because I cannot use irrational numbers as exponents, we just label the constituent distinct irrational charges as T1 fugacity and T2 fugacity. So you could rescale it to something which is integer here, but I'm just introducing more U1R fugacities for unique R charges that exist in this context, right? So that's why I have two fugacities. Yes, very good question. In general, I should have only a single fugacity, but because some of the charges are not expressible, that's why I use a refinement in terms of distinct R charges. So now going back to a dimension lower for the last 15 minutes, is that we did the same analysis from geometry to Quiver gauge theory in the context of Calabi free-folds, when we were looking at classifications of 4D n equals 1 theories. And now, in fact, this is something that we are going to publish hopefully soon, is I can now add green arrows to this picture, where in the context of 4D n equals 1 theories, these birational equivalences between associated Torre-Calabi free-folds also exist. And also in the context of 4D n equals 1 theories, this three observations that we made in terms of mass deformation, U1 R symmetry, refined Hilbert series, and the number of generators, these three properties also hold in the 4D n equals to 1 case. Not going into much deeper into that analysis, I want to tell you a little bit about another invariant that we recently discovered coming from this birational equivalence of associated Calabi manifolds. And that other invariant is connected to the integrable system that is naturally associated to the bipartite graph, defining the type 2B brane configuration associated to a brane tiling. In fact, every brane tiling realizing a 4D n equals to 1 theory connected to its associated mirror curve of the Calabi free-fold is representing a diamond integrable system, a classical integrable system that can be quantized, that is parameterized in terms of the path algebra that can be defined along the edges of this diamond graph. In fact, earlier I told you that this diamond graph tells me about the structure of the type 2B brane configuration, but the combinatorics of this brane configuration naturally also gives rise to an integrable system. And in fact, every non-trivial winding path along the edges can be associated to one of the terms or combinations of one of the terms in the corresponding Newton polynomial and mirror curve. In the context of the associated integrable system, these non-trivial paths along edges correspond to either Casimir operators, or they can correspond to one-loop operators of the associated diamond model. And using these Casimir operators and one-loop operators, I can also write down the associated Poisson structure of the integrable system. And in terms of the one loops, I can also write down the associated Hamiltonian of the integrable system, defined uniquely through the combinatorics of the diamond model. The neat thing is that now when I look at two Torre-Calabi free-folds that are related by this birational transformation, and the fact that these two toric varieties are birationally equivalent to each other, gives me naturally two brane tilings, diamond models, that define with their associated Newton polynomial two integrable systems. In fact, you can write down the Newton polynomial really being now the spectral curve of the integrable system. And now you can see that the birational transformation acting on the Newton polynomial is mapping the spectral curve of one integrable system to the spectral curve of another integrable system. But it's not just a map. In fact, you can use this map to map not only the spectral curve into each other, but each of the Casimir and one loop operators of the integrable system. What? This? C is conifold. Conifold over Z2 times Z2. It's one of the Torre-Calabi free-folds. Okay. Thank you. Yes. So these are two Torre-Calabi free-folds. They have an associated dimer graph representing two 4D n equals to 1 theories. They share the properties that I mentioned earlier. They can be mass deformed into each other. They have the same U1-refined Hilbert series. They have the same number of generators. But now, as dimer integrable systems, they share the same spectral curve but, by a birational map. But not only that, they share the same set of Casimir and one-loop operators, which satisfy the same set of Poisson structure relations, meaning that these two integrable systems are not only mapped into each other, they're equivalent to each other, right? Because they satisfy the same Poisson structure and they satisfy the same basis of operators that are mapped to each other by this birational transformation. So this is the fourth invariant that we are looking at here. Now, for brane tilings and Calabi free-folds, the birational equivalence between the associated Torre-Calabi free-folds implies that the associated integrable system defined on the brane tiling itself is in fact invariant to each other. So it's a very strong statement, and in fact, it seems to be true. In fact, we have been classifying all of the dimer integrable systems associated to these 30, 40 n equals to 1 theories, and they can be linked to each other by these birational equivalences between the associated Torre-Calabi free-folds, and we checked one by one that the associated dimer integrable systems are invariant between those brane tilings. So it's not easy to see that some integrable systems are equivalent to each other. In fact, our work is introducing the largest documented set. Hopefully, it's going to be out soon, but based on this earlier paper, it shows a large set of integrable systems that are equivalent to each other, and that classification really shows us the power of these birational transformations that connect Torre-Calabi into each other. So this really closes the loop here, right? I have been talking about new phenomena that happens in the context of Torre-Calabi in various dimensions. We reinterpret this new phenomena in the context of associated quiver gauge theories. But the new phenomenon is based on the associated miracles related to the Calabi-Yaos. And these miracles tell me what the brane configuration is that realizes the associated quiver gauge theories. Right? I have been showing you how we were using generative AI to generate projections of the mirror curve to identify associated gauge theories. So really, there's a triality of relationships that we are trying to explore, mainly now with this new context of birational transformations. And in fact, this is really a part of a larger program of trying to unify phenomena across different dimensions, phenomena that are related to Calabi-Yaos in different dimensions, as well as quiver gauge theories in different dimensions. And as you can see, I have not been talking about Calabi five-folds and zero-dimensional matrix models associated to them. Hopefully that will be a topic of some future talk in the future. But with that, that's the end of my talk. Thank you for your attention.
Thank you for the nice talk. Are there questions? Yes.
Thanks for the nice talk. So you mentioned that some of the birational transformations correspond to mass deformations, but not all of them.
Yes. Yes.
But more generally, one could consider just relevant deformations of
Exactly,
the CFT.
yes, yeah.
Do those fill in the missing?
Yeah, in the Calabria-free context, that was one work that I forgot to cite here. That was a work by Stefano Cremonesi, where they classified, for at least for the brain tilings associated to reflexive polygons in two dimensions, the associated marginal and relevant deformations of the corresponding 4D1 series. And then we saw that that is actually connecting to the other birational transformations that we are not seeing by normal mass deformations in general. And then we found that in the context of Calabria free force, at least, there's a mathematical understanding in terms of the diamond graph that generates these marginal deformations and the larger birational class of deformations that act on diamond models. That's why I didn't talk too much about the Calabria free context here. In the Calabria 4 context and the 2D 0,2 theory case, that's something that is not published yet. Hopefully by next week we will publish it, where we study a larger set of deformations of associated 2D 0,2 theories that relate to the other birational transformations that we have not been seeing so far in the 2D 0,2. So yes, the answer is yes. I don't know whether that will be enough to cover all birational transformations, and that's still an open question, whether there are other birational transformations that we still do not understand in the context of the corresponding gauge field.
Can I ask one follow-up on that? So then if you order the Calabi-Yaos according to who has the highest central charge for the GLSM and who has the lowest, is there like a large number that have a big central charge, or is there one and they flow to many different?
Also, that's something, also, so I cannot tell you much now, but that's something, we are also looking into.
Okay, I see. Thank you.
Yes. The interesting thing is that in 2D 0,2 context, there's the formula by Bernini, etc. But we are trying to understand what is really going on in terms of the dynamics of the 2D 0,2 theory in this context. Yeah, it's all related.
Other questions? So,
yeah. Can you use these AI methods that you used for the brain tilings also for the brain bricks?
Yes. So that's not published yet, but yes, that's what we are looking at. And they will, if I change the complex structure moduli for the Calabria fourfold curve, then that is basically generating the triality phases of the 2D 0,2 theory. So the simplest example is Q111 over Z2, the cone over Q111 over Z2, that is related to 3 distinct 2D 0,2 theories that are mapped into each other by triality.
And both there and also for the brain tilings, these dualities or that you see in this way, would you not be able to infer this without the AI techniques, or is this reproducing?
I could. The point is that finding these projections manually is not very easy, so that's why I can now use just a subset of the solutions to these equations defining by the mirror curve. And using that subset of solutions, the AI model infers the entire structure of the surface that is projected on T2 for any choice of complex structure model. So that's why I can then infinitesimally change the complex structure model to actually see how the brains move. So that's why I use generative AI. And the reason why I also wanted to use this was how the complex structure model actually parameterized the phases of the gauge fields, where at what boundaries of the complex structure moduli does Sieberg duality happen. And in order to do that, if I end up having many complex structure moduli, the moduli space that I have to traverse to identify these spaces will be very computationally hard, and that's why I use AI to make the computation much faster.
So speaking of this leather thing, so on what basis have you chosen this particular subsector within this higher dimensional moduli space? Was it just to see like, so for example, in your case, you had like C123 out of a lot of complex structure, and then you swept within this.
You mean for the generative AI model?
Yeah. Sorry,
Okay, sorry.
Just for curiosity.
So yes, so
you
I
may-
just fixed one basis. The important thing is that for any given calabi-Yau, there's a minimum number of complex structure moduli that I need, or that is enough to parameterize the mirror curve. And using that number, I can parameterize in whatever basis that I want. Right? The important thing is that I fix the basis and then change the complex structure model.
But that's only exploring some high codimension subspace of the entire moduli space. Am I right?
Well, it's the independent subset. Exploring that one is enough to know the entire structure.
So then, can you? So we can.
So, for instance, if I look at the Hitzebuch F0 case, I don't know, it's many pages before, but.
So this way you won't miss any transitions.
Exactly. Yeah. So
Sure.
so for instance, here I have so this is a calabi-Yau 4 case, but here I have in total 7 vertices, so 7 terms. In principle, I have for each term a complex structure moduli, but there's a theorem that only 3 of them are independent to each other. So I only need to fix 3 of them to understand the independent subset.
So that's always the same as the dimension of the.
No, it's the number of terms minus the dimension of the calabi-Yau. So this will be 7 minus 4, which is 3.
Okay.
So in the F0 case, I had 5 terms, calabi-Yau 3, so it was 2.
Yeah, thanks. I don't see any more questions. Then let's thank Rak again for the nice talk.